Attention car shoppers. Right now at South Carolina Federal Credit Union, you can get a new or used auto loan and pay nothing until 2024, and no payments for 90 days means nothing out of pocket going into the new year. Plus, we have flexible rates and terms, so you could make the best financial choice for you. Learn more at scfederal.org/auto loans. That's scfederal.org/auto loans. Certain restrictions apply. Existing South Carolina Federal credit loans are excluded.
Experiences are what people love the most about travel. That's why they love Viator. They have over 300,000 bookable experiences and something for everyone. Plus, their travel experiences have millions of real traveler reviews, so you have the information you need to book the best activities for your trip. Download the Viator app now and use code Viator10 for 10% off your first booking in the app. One app, over 300,000 travel experiences you'll remember. Do more with Viator.
Hello again. Thanks for joining us. This is Space Nuts, where we talk astronomy and space science. My name is Andrew Dunkley, your host, and this is an all-question episode. Well, almost. We'll be hearing about spin launch. Somebody's not so much sent a question in, but they've been there and wanted to tell us about it. But questions about the radial velocity of stars, negative gravity, dark matter, and the Casimir effect, and much, much more coming up on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining me as always is his good self, Professor Fred Watson, astronomer at large. Hello, Fred.
Hey, hello, Andrew. Good to see you again. It seems like years since we've spoken.
It could be a year, it could be a week. I'm not sure which.
Something like that, yeah.
Whichever's the shortest.
It's the end of year phenomenon where you really don't know whether it was last year or last week or both.
Or what is up or what is down. Yeah.
Exactly.
How you been? How are you?
Very well, thank you. Not quite traveling as widely as last week and the week before, but I've been in Canberra for a short sojourn. Came back yesterday afternoon. It was freezing down there, Andrew. The temperature was
freezing here.
10 degrees. Yeah.
Well, we've because I looked it up, and I know why we're so cold and wet in this part of the world now. But basically, it was the Tongan volcano which put all that moisture and ash and dust into the air. So the ash and dust created a blanketing effect and kept the temperature down. But the billions of litres of water it put into the atmosphere has caused all this rain, combined with the La Nina effect, which is why we've had those catastrophic floods on the East Coast. So, but as a consequence of that, we are having December temperatures that are 10 below where we'd normally be. Like we haven't got into the 30s more than once or twice this year so far, and it's usually, end of October, early November, we hit some big numbers, and we just haven't been there. It's been extraordinary. And they've had snow in December further south.
Yes, I heard that.
Amazing. Now, we've got a lot to get through, so we might as well get stuck straight into it. And our first listener is John from New Mexico. Now, John is not so much asking a question, but he's been somewhere very interesting recently and wanted to tell us about it.
Hi, guys. I'm John from New Mexico. I have a cabin up in Cloudcroft, which is near Apache Point and Sunspot, about 9,000 foot elevation. Fred might be aware of it. I had the opportunity of touring today the spin launch facility at Spaceport America, and I heard you discussing it last week in response to a question. It's an amazing off-the-shelf type technology. Quite impressive. Andrew, if your wife wants to insist you come to New Mexico or travel a little bit, come see us around the Spaceport America Cup. Last year, University of Sydney won first place. In the modeling division, University of Melbourne was first place, and the runner-up is Monash. There were teams from all over the world. It is hot out there in the middle of the desert, but I think you would enjoy it, given your propensity for all things space and technology. In any event, I do enjoy your show. It's great. So I always move it up on my podcast list. Thanks. Have a great day.
Thank you, John. Thanks for those kind words. And I reckon checking out the spin launch facility would be extraordinary.
It would.
And we're talking about technology that's designed to fling satellites into sub-orbit, but it's designed to reduce the amount of fuel required. They don't really cut the engines in until they've thrown it up into the stratosphere or something.
That's right. And
amazing.
And in fact, the question we had on it was about whether you could deploy it on the moon. That's right. The spin launch speed that we read about matches the moon's escape velocity, so you probably could. I've visited Spaceport America, but it was quite some time ago. It's probably 2016, I think, if I remember rightly, and I never saw any trace of the spin launch facility.
No,
but it will be something interesting, to put on the to-do list next time we're in the States. And John's mentioned too of the Apache Point Observatory. That's a very well-known place in astronomical circles. It is where the Sloan Digital Sky Survey took place, if I remember rightly. I hope I'm getting my facts right there, but I think that was at Apache Point.
Yeah, fantastic. Well, lovely to hear from you, John. Thanks for passing on the info. And please, if you get a question in mind that you'd like to pass on to us, we'd love to hear from you again. We get a lot of repeat offenders, and we do have one now in the form of Rusty from Western Australia.
Hello, Fred and Andrew. It's Rusty in Donnybrook. Fred, your work combining the AAT's radial velocities of stars with Gaia's proper motions has given us true velocity for thousands of nearby stars. Thank you. Have we used this data to compare the average velocity of revolution around the galactic centre for older stars outside the influence of spiral arm density waves with that of stars in a spiral arm? I suppose we'd be looking at local G and K stars and hot young stars in the Orion arm being the closest arm. It would be good to know how the pattern speed compares with the general revolution in our precisely measured local area, and see if the differential is what we expect at our position halfway between the centre of the galaxy and the outer rim. Thanks for a fantastic show, guys. Cheers.
Thanks, Rusty. And
thanks for a fantastic question.
Yeah, it's a ripper. You might have to sort of take it apart for us so that we know exactly what he's referring to, but it sounds like it's work you've been involved in.
Yeah, although more peripherally than I think Rusty imagines. My involvement, the main survey I was concerned with was something called RAVE, the Radial Velocity Experiment. This is the main star velocity survey, which ran from 2003 to 2013. And we surveyed the speeds along the line of sight of about 500,000 stars with reasonably high precision, kind of getting down to a kilometre per second, which for the tiny piece of equipment that we had on the UK Schmidt telescope, that was fantastic. On the Anglo-Australian telescope, the big survey is the Galar survey. Galar is Galactic Archaeology with Hermes. Hermes is another acronym for the instrument that was used for this. Still operational, still doing great stuff. And in fact, the Galar survey is still in action. So, Galar does deliver velocities, as well as its main mission was to look at the chemistry of stars within the sun's neighborhood by analyzing the chemical elements there. I think 20 particular elements were what were pinpointed, if I remember rightly, but the velocities come out of that. Now, throw that into the mix with the Gaia proper motions, which is the motion of a star across the line of sight. And so if you've got the motion across the line of sight and you've got the motion along the line of sight, you can do some fairly simple mathematics to get what's called the true velocity, or the actual velocity of the star. And that's what Rusty's asking about. Now, the sorts of studies that he's talking about, looking at the old and young populations, the young population definitely belongs to the disk of the galaxy. These are stars that have been disturbed by the passage of the density wave that causes the spiral arms through the galaxy. What Rusty referred to it as the pattern speed, and comparing that with the old stars that are of the older stars that are also in the sun's neighborhood. Now, we used to think that the galaxy was in two parts: the disk with young stars in it, and that halo, spherical halo with old stars in it. But that, thanks actually to work by people that I've worked with on these various radial velocity experiments, because I'm also involved very peripherally with the Galar survey that used to observe for it a long time ago. The studies that have been done indicate that two-phase model, a disk and a halo, is kind of wrong, because that's probably 15 years ago. Some of my colleagues on both those surveys, Rave and Galar, realized that the disk is not a simple structure, that it's got two components to it, which are named in characteristically straightforward fashion: the thin disk and the thick disk. And there is an age difference in those populations of stars, as well as there being a kinematic difference. And what I mean by that is exactly what Rusty's talking about: the motions, the way the motions differ. Now, what I suggest, the work that's ongoing on that is still part and parcel of frontline research in the dynamics, the movements of objects within our galaxy. So Rusty might advantageously check out thin disk and thick disk, and perhaps Galar too, GALH, on the web to see the insights into these velocity differences that are being looked at. So, and I'm sure he will find a much more cogent answer to his question than what I've been able to give at the moment. But the basic answer is yes, astronomers are looking at that. It's exactly the kind of thing that's of interest in understanding how our galaxy was put together and how it's evolved.
Yeah. I read the other day, Fred, that beyond those two, let's call them hemispheres, whatever, disks that you talked about, they've found another layer that could be dead stars. So when stars they just get, ejected, and they've become another population out there. I don't know if you've heard about that.
No, I haven't. But dead stars come in many, many different shapes and sizes.
Yeah, they do.
Depending on their initial mass. And you usually expect that dead stars will continue to be members of the population that they were part of when they were, when they were active. So that sounds a bit unlikely to me, but I'm interested to follow that up.
Yeah, if I can find it, I'll let you know.
Oh, thank you. And if you can't, no, that'll be.
Sometimes I read these things and then they disappear into the ether. Yeah, but yes. I found it fascinating. Speaking of thin discs, that would describe the top of your head, would it not? Better than being a thick disc.
Yes, well, that's right. Well, yes. I mean, there are various nuances to the word thin, and when it comes to hair, you're quite right. In fact, even the word sparse doesn't actually cover it for the top of my head. It's just gone.
We're talking, rather than sparse, it'd be parsecs.
Yes, that's right. Yeah.
Oh dear. Did we finish answering Rusty's question?
I think so. Yes. I hope Rusty feels that was worthy of his question, which is a great question. And once again, like so many of our listeners, these are thought-provoking and very intelligent questions.
As we always say, Rusty, we covered it adequately.
I'm not sure about that.
Adequate answer. Thanks, Rusty. Let's move on to this one, which is a fascinating topic because it is one of the things, it's one of the fundamental forces of nature, but it's also one that throws up so many questions because we don't absolutely understand it, and that is gravity. And this is a question from Daniel.
Hey, Daniel here from Melbourne, Australia. Just a question. If gravity is detectable around large mass bodies, could there possibly be negative gravity where there is no mass? So generally, there's a negative to most positive forms of energy, so perhaps negative gravity is an area void of mass, e.g. the expansion of space accelerates away from mass and gravity, so could the force driving said expansion be negative gravity? Answer that. Thanks.
Yeah. I don't think we've ever had anyone ask about negative gravity before. I mean, we've talked about gravitons being a potential particle that we've never yet discovered, but and we talked about gravity a lot and its effect on space-time, but negative gravity, never really gone there.
No, that's right. And so it's absolutely right. Daniel's quite right that things like magnetism, electromagnetism, you have opposite poles, you have antimatter, which has an opposite electrical charge to normal matter. With all these things, and we maybe could counterintuitively expect there to be negative gravity. And by that, I mean, a gravitational force that repels rather than attracts. I suppose the analog, and certainly early physicists saw this as an analog. When you bring like magnetic poles together, you get a repulsion between them, and some people have looked at that. And I guess that would be what you might call negative gravity. There's been a lot of study done on the idea of anti-gravity, which is not quite the same thing. What that is all about is gravitational shielding. Sometimes it's called a non-gravitational field. So the idea is, and again, this is absolutely hypothetical, that you create something where there is no gravity. So you kind of build a wall around it, an anti-gravity wall, and you've got no gravity. And I think it's, you would know this better than me, Andrew, I think it's played quite a significant role in science fiction, the idea of fictional anti-gravity vehicles, for example, and things of that sort, which would be a great way of sailing around the world. And maybe that's, to some extent, that's more like, I think, what Daniel's alluding to, the idea of where there's no gravitational field at all to speak of. Have you got effectively an anti-gravity shield? And the thing about gravity is that it's a bit like electromagnetic radiation. It's got infinite reach. It doesn't just fall away to zero very quickly. And so I suppose you could argue that there's nowhere in the universe where there is no gravity, even though we know that the intergalactic space, and in particular the space, the voids, if I can put it that way, in the what's called the cosmic web, which is this sort of almost like a froth or foam of structures defined by clusters and sheets of galaxies. Within the honeycomb, the empty honeycomb cells of that cosmic web, that will be a place where you could say there's gravity is negligible, even though the overall gravitational potential of the universe needs to come into it. So I can't actually remember what Daniel's question was, but these are all concepts that really have remained in the field of the hypothetical. A lot of work has been done on this, and in particular, it comes out of the studies of general relativity. General relativity is the best, and probably you might put it this way, the only theory of gravity that we've got that holds up, and it holds up incredibly well. It describes gravity in great detail, but it's still, the bottom line is we still don't know what it is. It's probably the least understood of all the fundamental forces, and the idea of gravitation, I think, whilst we can see how it behaves, and relativity describes that perfectly, we don't have a quantum theory of gravity, so gravitons have never been discovered or never even been properly theoretically described. So it's still a very, very open field. Wouldn't it be fabulous, though, if there was a breakthrough and somebody managed to produce an anti-gravity cage or even an anti-graviton, which would force us in the opposite direction from gravity?
Oh yes, would be amazing. I just and it's one of those things that's so hard to get your head around because you don't know why it's happening. You just know it's there. It's
yeah, that's right.
yeah,
and kind of just as well it is, because galaxies wouldn't have formed and stars wouldn't have formed without it. So it is very useful to have gravity. We wouldn't be here without it.
It's pretty handy stuff.
But wouldn't it be brilliant if you could control it? That's the bottom line. If you could if you had a knob to turn that changed gravity.
Yeah. I suppose we may be able to one day, once we figure out what it is and what the driving force behind it is, and how to harness that power. But then again, if humans could harness the power of gravity, that'd be pretty scary too.
Yes. Yeah. When you think of what humans are capable of, absolutely.
Yeah. We always seem to find a way of turning something good into a weapon or something like that.
Exactly.
Because there have been a couple of major announcements this week in regard to scientific leaps forward.
Yes.
They've made a huge advance in the potential for quantum computing, and that is because they've been able to direct light in both directions of time simultaneously, which I find extraordinary. And what was the other one I heard about?
Probably the fusion reactor. The
fusion
fact
reactor,
that we've for the first time at Lawrence Livermore Laboratories, a fusion experiment has taken place where more energy has come out of it than they put in, and that's a huge step forward. Huge.
And you know what they used for that?
Yeah, lasers.
No, celery.
Oh, celery. Okay, of course. I overlooked the celery. I thought
celery. It's one of the only foods you can eat that will help you lose weight because you use less energy to digest it more energy to digest it than it provides. Something like that.
There must be other.
Look it up. It's true.
Yeah. Is it the only thing? I mean, what about?
I think it's.
What about oats and bran and all of that stuff? Don't you have to work out?
No, I don't know.
Yeah. Anyway,
I don't know.
That's not really
not the same thing.
The same.
But being able to create more energy by using a laser that doesn't require. You're basically creating more energy from a lesser source of fuel, which
that's right.
Usually goes the other way. The fuel
it does
burns, and there's so much wastage.
And that's the point about fusion, that once we achieve fusion as a routine thing, and I'm sure it will happen, then we've got a very, very good, useful and clean source of energy. You probably know about the other big experiment that's going on with this in the south of France. It's called ITER. The T is I think the I is international, T is thermonuclear, because it's the thermonuclear reaction that they're trying to set up. But they're building a device that is attempting to do the same thing, but rather than using lasers to create the environment in which fusion takes place, and we're talking about sticking atoms together to change their properties and turn them from hydrogen to helium. That's the bottom line. That's using magnetic fields rather than using lasers. It's in fact, I once met somebody who worked there, a gentleman who was a friend of a friend. He also has a farm in the south of France, but he works at the ITER facility too.
Amazing, isn't it? Yeah. I think we're really on the cusp of some major.
Well, I believe we are too,
stories.
But I go through life believing that.
Well, look at the technology today compared to when you were writing on parchment.
Yes, indeed. That's right. It's papyrus, actually. In my
papyrus.
Yeah.
Oh dear, we could really cash in on that joke, but we won't. We'll take a breath and we'll answer some more questions.
Sounds good.
Here on Space Nuts.
1.
Space Nuts.
Now, Fred, to our next question. This one comes from Michael, and it is surprise, surprise, about dark matter.
Hey, Fred and Andrew and listeners. My name is Michael. I'm from Toronto, Ontario, Canada, and I have a dark matter question. Seems you get a lot of these here on your lovely podcast. I know that there have been some hypotheses about how dark matter could be explained away, including by accounting for relativistic effects of massive objects as they move through space-time, but that these theories fail because their contribution is too minute to account for what we observe about galaxy and cluster motion. Celestial objects are moving, and we know that increasing the velocity of an object increases its relativistic mass. But as we go up the ladder from minuscule objects to astronomical ones, could highly relativistically modified systems have consequences for distant observers? Imagine a very massive star orbiting the center of a galaxy that is not quite massive enough to be a black hole. Could such a star at least apparently cross the mass threshold to becoming a black hole if relativistic effects are accounted for? If so, could there be a difference in how it appears locally versus at a distance where observers are moving more slowly?
Wow.
Thanks, guys.
Wow. That's a deep question, very thought-provoking, and very well thought out too, I might add, Michael. Gosh. So where do you start with that one?
So we're talking about reference frames here, about, how and that's the key to understanding relativity, that you're the way something behaves in a reference frame that you're observing but you're not part of is what you actually is where a lot of these phenomena occur. And Michael's right that the local effects are seen from imagine looking at a moving object from a stationary rest frame. Then that's when the moving object displays all the curiosities of relativity, like time dilation, and the Lorentz Fitzgerald contraction. That means its length contracts as it in the direction that it moves, and the increase in mass. But to the excuse me, Andrew, to the moving object in its own reference frame, everything stays the same. And so it's certainly in terms of tripping over a near black hole mass object in its moving reference frame, that doesn't work because it's only to the observer that this looks as though it's the mass has increased. Having said that, of course, the effect of it on its surroundings are the effect that the observer sees. So I'm talking now about things like orbits. There's some really interesting thinking there, Michael. I'm not sure that these relativistic effects would account for the dark matter phenomena that we see. And relativity, both kinds, both special relativity and general relativity, are absolutely second nature to astronomers. No matter what they do when they do calculations, that relativity comes into it. And so it seems unlikely that such a really interesting interaction of relativistic considerations would have been missed by the colleagues of mine who are working on this sort of thing. And I think our friend and colleague Peter Verweyen, who works on one of the alternative theories for dark matter, that dark matter is not real, that we have instead modified Newtonian dynamics, he too is immersed in the relativistic considerations here. And so once again, I think it's unlikely that there would be anything that had crept in that was leading us in a direction that hasn't already been thought of.
Okay, wow. I did read something recently. They've had another crack at trying to put a dent in Einstein's theory of relativity and failed. So it continues to hold up.
It does. And that's, all credit to Einstein for hitting the nail on the head back in 1915. And all credit to the rest of us for trying to pick holes in it, because there is something that we're missing somewhere. Whether it's in the the fact is that we don't have a quantum theory of gravity, and that has eluded very gifted theoretical physicists for decades and decades, in fact, starting with Einstein himself. So when that comes, and I believe eventually it will, then the answers to a lot of these questions might look a lot more obvious, or at least a lot clearer.
Indeed. All right. Thank you, Michael. Let's move on to a question from John. This one's probably as mysterious.
Yes, this is John Mayer in the west coast of Canada, and I was wondering if the phenomenon that causes the Casimir effect would be responsible for the acceleration of the expanding universe. Thanks very much. Love the show.
Thank you, John. Love the voice. Now,
Yes,
the Casimir effect, you might have to try and explain that so we can tackle the question.
Yes, so it's a physical force which it basically acts when you've got a confined space. So if you imagine, and this is the way it's normally, normally formulated. If you imagine two parallel plates in a vacuum, just sitting there minding their own business, then there is basically a physical force between them, which was predicted actually by a Dutch physicist. His name was Hendrik Casimir, back in 1948. And it comes out of electromagnetism, but it is a quantum effect. So that this force actually pushes the plates, tries to push the plates together. It comes about because at the quantum level, the vacuum's not empty. It's got all these fluctuations in it. We talk about, in fact, we'll talk about it in a few minutes, I think, the idea of virtual particles and things of that sort in the universe, which come from these vacuum fluctuations. So it's sort of connected with the electromagnetic force, but is actually a quantum effect that it actually, you don't have to have for example, you can have an atom that doesn't have any magnetic or electromagnetic field, and yes, that will still suffer from or experience the Casimir effect. There is actually there's a very complete article on the Casimir effect on Wikipedia, which I'd recommend John and anyone else who's interested to have a look at. But of course, this sort of thing is the first thing that was looked at when the universe was shown to be expanding at an accelerating rate. There is one calculation which is along similar lines to this, but suggests that there should be a repulsive force in the vacuum. But and very famously, that force comes out to be 100, not 120, but 10 to the power 120 times too big. So that if that was correct, it would have ripped atoms apart at the dawn of the universe, and nothing would have ever happened. And it's often quoted as being the worst prediction in physics, because there is clearly something driving the accelerated expansion of the universe. We think it is a property of space itself, a bit like the Casimir effect is. And so I suspect physicists have the first thing they did was look along these lines at the vacuum fluctuations and that sort of thing to see whether that could account for what we observe on the large scale in the universe. And the answer is, if you do the sums in the way we normally do them, you get an answer that's far too big. So it can't be that. So there's something else going on here. But good thinking, though, on John's part. Casimir effect is itself mysterious. It works and is understood in terms of quantum field theory. But it's one of these things that it's a bit hard to get your head around, Andrew, as you can probably tell.
I reckon Daniel answered it for John. It's negative gravity.
Well, there you go. That could be it too.
Could have been. All right, John, thank you so much. And I'm looking forward to visiting the west coast of Canada middle of next year. So, that's going to be 3 years overdue. We're supposed to be there 3 years ago, but we're finally going to get there. Fingers crossed.
Good.
Should be fun. This is Space Nuts with Andrew Dunkley and Professor Fred Watson.
0G, and I feel fine.
Space nuts.
Now, let's tackle our last couple of questions. This first one has come from one of our regulars, Buddy, who is talking about, of all things, golf balls.
Hey guys, Buddy from Oregon again. I was listening to a past episode, and you were talking about golf balls and Mars. And I'm willing to bet, if you think about it, I'm willing to bet $1 on it even, that a golf ball is going to travel a lot further on Earth than it does on Mars.
Mm-hmm.
I think the air keeps golf balls aloft a lot farther than most balls. And with thinner air, it isn't going to fly. All right, thanks, guys.
Okay. Thanks, Buddy. I see where he's coming from. Now, they've done the experiment on the moon where they hit 2 golf balls, and they went a lot further than they did on Earth because there's no atmosphere. There is atmosphere on Mars, but it's a lot thinner. But the gravity is also lower. So lower gravity would equate to a longer golf shot with the same club in the different circumstance. But would the thinner atmosphere actually mean the ball could not fly as far? I think that's where Buddy's going.
It is. And you're probably more... you're absolutely right. The gravity on Mars is only a third of what it is here on Earth, and that will be the overpoweringly dominant effect, I think, in terms of the golf ball. But you are the expert, I think, on the aerodynamics of golf balls, and that's why they have the dimples in, isn't it? So that is. So that they actually get some lift.
You know how they discovered that? Because in the early days of golf balls were smooth. And if you could, and they flew off in all directions. They had no real control over them at all. To hit a straight golf ball back then was virtually impossible. But they discovered that over time, if you didn't lose it, they became scuffed and marked and dented and scratched. And suddenly they were easier to hit. They flew more true. And that's where they realized that something aerodynamically was happening to the golf ball. So voila, the dimple was invented. And of course, now they've been experimenting with all sorts of dimples. The early golf balls had the same size dimple all over with no pattern. Then they started doing patterns. Some of them got hexagonal dimples. Now they group them in different sizes. There's all sorts of stuff going on. But the bottom line is the dimples create an aerodynamic effect to keep the ball aloft and to go straighter. That doesn't answer the question as to whether or not it would go further or shorter on Mars. But as you said, gravity being the most likely controlling factor, you'd have to say that a golf ball struck with a driver on Mars would go much further than it would on Earth.
Yeah, so Buddy's raising the counter argument to that, and yes. I think so. From what you've said, it sounds to me as though the dimples, and I didn't realise that that they were changing the shapes of them as research goes on. I should take a look at the golf ball these days.
They're actually talking regularly about changing the rules to control the development of the golf ball because it's getting way too controllable.
Yeah. Well, that's what I was about to say, that it sounds to me that as though the dimpling is all about the control of the direction of the golf ball. It's the sort of flight control rather than getting much lift from it. So there may be some lift that comes from the interaction with the atmosphere, but it sounds as though it controls the real thing. It's like the difference between, the wing of an aircraft, which is what provides the lift, and the ailerons and elevators that actually give you the control over it, over that lift. So the dimples maybe give you the control, let you hit the golf ball in a particular direction rather than any random direction, as I'm sure you're very well aware of, Andrew. So I think
notwithstanding the wind effect,
I think between us, you and I are mounting a counter argument to Buddy's argument, and I think we're probably going to have to wait until maybe the late 2030s when somebody does actually hit a golf ball on Mars.
See where it
goes. Yes.
Yeah, it could be. Yeah, it's interesting when you try to understand how a golf ball works in the air, how much science there is in it, because you've also got to account for the wind. You've also got to account for the gearing effect of the direction of the movement of the club at impact. and the gearing effect will offset the axis. And so if you hit the ball from an inside path, and let's assume my fingertips joining is the equator, if the ball tilts on an inside axis, it will fly right and then draw left.
Right.
If you hit it from an outside swing direction, the gearing effect puts it on that tilt and it flies right for right-handed players. So you've got all of that comes into play. So it's not as simple as just putting dimples on the ball and it'll go straight. There's so many other factors. But and I have not mastered it.
Is that because it's spinning, Andrew?
Yes.
Yeah. So it's the spin that you impart.
So it's like the wheel of a bike.
Yeah.
When you tilt a bike to the right, it goes right.
Gyroscopic effect.
You tilt a golf ball to the right, it goes right.
Yeah.
It's the same thing.
There you go. I didn't know that.
Yeah. See, we've got a lot in common with cycling.
And quantum physics as well, because it's all about spin. I'm slightly ashamed that I spent my formative years at the place in the map behind me, the home of golf at St Andrews.
Yeah.
I lived there for a long time. And never ventured on the golf course because I thought it would distract me from my studies. So I learned to play the guitar instead, which distracted me from my studies.
As it does, yeah. I've never. It's one of my bucket list things is to go and at least have a look at St Andrews.
It's a lovely
love
place.
to get a game there. Love to get a game there, but it's just so hard because of the waiting lists. And but buddy, Fred and I think probably more to do with gravity than the atmosphere. So a golf ball on Mars most likely would go further, and I could certainly use that.
Yes.
Okay. Let's go to our final question, and this is a text question from Kiefer. Hello, Andrew and Professor Fred. I love the podcast. I get to learn and laugh at the same time. We'll stop doing that. A rare combination. My question is regarding black holes. How can black holes emit particles beyond the event horizon that can be detected? My understanding is that the gravitational force of a black hole creates an escape velocity greater than c. Since nothing travels faster than c, we cannot know for certain what is happening in a black hole since no information can escape. Then why does it seem black holes literally defy the universal constant by emitting particles? My question was stimulated following a review of the article, he sent us a link, about relativistic jets and an energy beam. I hope my question makes sense. Keep up the great work. You remind me every episode how little I know and excite me to learn more. Sincerely, Kiefer from St John in Florida. Thanks, Kiefer. It's a great question, and Fred knows everything about black holes there is to know, which is not much.
That's right. Yeah, well, I think every episode reminds you and I how little we know as well.
Yeah.
So this is the classical question, and it's certainly true that in terms of relativistic physics, nothing can escape from a black hole because exactly for the reason that Kiefer said, the gravitational potential is too high, and so the escape velocity is greater than the speed of light. However, there's a little bit more to stuff than just relativistic physics. There is something called quantum physics, and that's what Stephen Hawking brought to bear when he considered this issue in the 1970s. It's what actually put him on the road to stardom. The idea that there is a way that radiation can escape from a black hole, and it's all about what we were talking about earlier in relation to the Casimir effect. If you've got a vacuum, quantum physics says you've got virtual particles popping in and out all the time, and if the vacuum is sort of neutral and empty, these are in pairs, so you get positive and negative particles popping out. And the idea is that in the region around the event horizon, when these virtual particles pop into existence, if they're too near the event horizon, one of them will get sucked back into the black hole and the other will wind up being lofted into space. And so it becomes an emission of radiation. In fact, the particles in question are photons, because this so-called Hawking radiation is an electromagnetic radiation. It's photons that come from the black hole. and eventually will take away the energy of the black hole and the mass and lead it to evaporate. But the time scales for that evaporation are billions of
squillions.
Billions of times the age of the universe. It's not just squillions of years. So it's a very slow process. Actually, it might not be billions of times. It's certainly well in excess of the age of the universe. The other side of this coin is that, okay, if this radiation is taking place and we know it's electromagnetic radiation, can we observe it? And it's never been observed because the theoretical calculations say it's too weak. It's such a slow and low energy process that it's not anything that we could see. So it hasn't been looked for, but you never know. Somebody might detect Hawking radiation one day. We've certainly detected analogues of Hawking radiation when you build models of these things.
Yeah, I actually read about one last week, I think.
Okay.
Where they've done it.
Yeah.
Which I was about to bring up, but you already covered it.
Oh, thank you. Well, I wish you'd just answered the question yourself. You could probably.
I don't understand it. How could I answer it?
What makes you think I do?
Yes, you've got letters after you.
I do.
That's
yes,
how I think you.
That's right. Post office box number. Yeah.
Oh dear. So, did we answer?
Well, we tried to explain why,
to the best of our ability,
why black holes can evaporate and why radiation does come from it. And in fact, that reminds me of something else I was about to tell Kiefer. The fact that you've got this radiation that comes from a black hole suggests that information can leak from a black hole, because the previous thinking was that when something goes into a black hole, it's totally disintegrated, so any information that it contained is lost. And Hawking had a bet with another famous physicist. I can't remember what the bet was. I think it was a bottle of something alcoholic, that information could not emerge from a black hole. And I think the theoretical consideration showed that it could, which Hawking had to concede the bet. I think I've got that the right way around.
Okay. Wow.
So there is a story to that. It's worth looking up. I should check it myself, so I'm not talking complete rubbish, but I do have something in the back of my mind about this bet.
That surprises me. I wouldn't have thought he was a gambling man.
Well, yes, that's right.
I think we all are at some level.
Well, in quantum physics, we've all got to be, because, it's what Einstein said, God does not play dice. That's why I didn't like quantum physics, because it's all about probability.
Yeah, interesting. All right, Kiefer, thanks for the fabulous question. Thanks to everyone who sent in questions and comments. We do love to hear from you, and please keep them coming. You can do that through our website, spacenutspodcast.com or spacenuts.io. Just click on the relative links, the AMA link or the Send Us Your question link, and you can send audio or text questions. Don't forget to tell us who you are and where you're from. And while you're on the website, check out the shop. Christmas is coming up. You might want to buy yourself or someone else a gift. You can also join our supporters through Patreon and Supercast. And thank you to all of those people. You are fabulous. We're so glad you like what we do, that you're willing to put your money where our mouths are. That's terrific, and we certainly appreciate it. And don't forget our social media platforms. We're on Facebook. We're on Twitter. We're on, other stuff. Oh, TikTok. Yeah, I forgot about that. And we also encourage you to join the Space Nuts podcast group, which is a user-generated group on Facebook where you can talk to each other and share each other's ideas and questions and answers and photos and who knows what else. It's a fun group. I do poke my head in occasionally. Fred, we are done and dusted for another week. Thank you, sir.
It's a pleasure. Always fantastic to talk, and getting questions like this is just it's great, isn't it? It's just terrific that we get such enthusiastic and intelligent questions from our audience.
I do love it when they can bring golf into quantum physics. Yeah, it's good stuff. All right. Thank you, Fred. We'll catch you next time.
Sounds great.
Bye. Fred Watson, astronomer at large, part of the team here at Space Nuts, and thanks to Hugh in the studio who had to leave early, so everything went really smoothly after that. And from me, Andrew Dunkley, it's goodbye until next time. We'll catch you on the next edition of Space Nuts, coming out real soon, but we've got to finish this one first. Bye.
Space Nuts. You've been listening to the Space Nuts podcast. Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.